Yes.
Yay. Okay, good.
I can see myself.
Nice.
All right. Welcome everyone to shaders, and this talk is for everyone. There we go. This talk is for everyone. It's for people who have never written shaders before. I hope even people who have written shaders will learn something from this. So I do assume that you know some stuff about Unity, you know how to make materials and shaders and textures and meshes and that sort of stuff. And I am using Unity for this talk, but I do think a lot of the concepts here will be applicable to any system. I mean, if you want to make a shader on Blender or some other engine, I think you could definitely learn some things from this and apply it to that as well. One note though, if you do want to use a different program, there's actually two different dialects of shaders that are in common use. One, this talk uses HLSL, which is what Unity uses, also called Shader Lab. There is a different dialect called GLSL, which is from the cross-platform OpenGL, and you'll find OpenGL in wide use in browsers, for example. So if you ever browse ShaderToy or other websites, Neort or any website that lets you upload shaders, you'll notice that that code's written in GLSL, and that's basically there's not a whole lot of major differences between them, but there are a lot of little things. For example, HLSL lets you get away with just about anything you write. Like, it'll do something, but maybe not what you want. GLSL is a lot more strict, so if you want a floating point number, like a float, you actually have to say like 1.0. There has to be a decimal point in there, so it knows that it's a float. For example, there's also some naming convention differences. It says mix instead of lerp, vec3 instead of float3. They're pretty similar, but it's good to be aware of the differences because I do think ShaderToy is a really amazing reference, and you should be comfortable looking through some of those code samples and sort of extracting what you want from them and converting them between HLSL and GLSL, because most of the changes are pretty minor. There's a lot of documentation online for this stuff too. And also, some people are going to be wondering, like, well, what about visual shaders, shader graphs and stuff like that? I didn't want people to have to pay money to write shaders, and Amplify is an amazing tool for Unity, but it does cost money. And I don't think you have to... Amplify is a great tool, but I don't think you should have to use graph shaders if you're just learning. I think you can learn just by writing code. And for most of the simple things I expect people to be writing, I think you'll be fine with code. And also, Udon has kind of pushed people in the direction of learning a bit of coding anyway. It is a bit tricky to learn programming for the first time, I understand that, but it's a lot simpler than even the type of code you'll encounter working with C# or Udon. Most of it just comes down to the math. It's all doable, so yeah, if you're afraid of coding, I think you'll be just fine here. But if you have Amplify, you want to follow along the graph, it's pretty similar. There's just basically make a lerp node or a mix node instead of writing the function lerp parentheses. So yeah, so shading. Let's talk about shading. Shading can make really beautiful scenes. Some of the most amazing content you've seen in VRChat is done with standard shader. Standard shader can make probably some of the most impressive looking content, physically based rendering. And so while light baking is really important and proper lighting is really important, shaders are not going to help you with either of those things. So if you're looking to make the really amazing content, this is not the talk for that. So that said, yeah, so this scene was made entirely with standard shader. There's no custom shaders going on here. So yeah, PBR exists for a reason. But yeah, so that said, when do you want to use a custom shader? So you'll find PBR tends to produce static scenes. I mean, it defines how something looks, but doesn't define any sort of animation. So if you ever want to animate something, or you know anything dynamic, you might want a shader for that. There's also some other common uses. I think pretty much every game or every map that has some water in it, the water is almost always using a custom shader. It's just one of those things that PBR doesn't really accurately describe how water behaves. So skyboxes, especially in Unity, skybox is kind of a weird, funky type of material. You would have to use a skybox shader for that. Toon styling, sort of a common example of that. Something that's not physically based rendering, it's your own custom shading model. You would want a shader for that. I don't know why I put particles here. Honestly, like additive blending standard particle shader can do just about most effects you'd want to do, but sometimes you want custom particle effects. And also, if you listened to Cyan Laser's talk yesterday, which was really, really interesting, you'll notice that they used a lot of this fake light shader in Devouring, and those sort of deferred shading is actually really powerful and definitely worth using, and it's really not too hard to use. So yeah, for any deferred effects refers to effects where you use extra information rendered for every pixel on the screen. In the case of the fake lighting, it's using the depth information, how far away each pixel is from the camera, and using that to sort of make it more dense or less dense fog depending on how far away it is. So yeah, that's an example of where you can use a custom shader to add something. Wireframes, other random effects also. So what does a shader actually look like? I don't know if you've ever double-clicked a shader file, but if you have, you've probably seen something kind of like this. If you have Visual Studio Code installed, which I highly recommend, or any other favorite coding tool that's not Notepad. So if you've ever double-clicked a shader, you'll see something that looks kind of like this. So what's actually going on here? Well, so first, you've got your properties. So this properties block is really good to know about. It's pretty straightforward. Everything in here just goes in the inspector. That's what it does. You can also make like custom headers. You can make, range, make sliders and stuff. This defines what goes in the inspector, and you can add more stuff in the inspector as you want. It's pretty nice. So then there's uniforms. Usually these will match one-to-one with the properties. So basically you have, you declare the inspector things, you can assign texture, assign a color, and then those textures and colors get actually put into the shader, so the shader could access that data. Now you have your V2F struct. I'll cover that a little bit more later, but basically this is the output of the vertex shader and the input of the fragment shader. And I'll cover what those mean in just a second. Also, just a little note, this example shader is quite short. Most shaders you open up will not be this nice and conveniently short to fit on a slide. This shader is unlit, which means it doesn't handle any lighting. It is just taking some pixels and telling the GPU to put that exact color on the screen without applying any lighting, and that's why it can be so short. An actual lit shader will have forward base pass, add pass, shadow casting, and each pass is going to have to do a lighting model, and it's going to be a bit longer. So this concise example is only possible because it's unlit. But I'll cover a way to do more complicated shaders without too much code later on. So don't worry too much if you don't understand all of this. I'm just trying to make you a little bit comfortable with when you open a shader file, the stuff there makes sense. It's just, there's a few different parts of it. So let's look at what a vertex shader actually does. So this was actually extracted from the previous slide. It's exactly what's in the vertex shader. So what is going on here? So first of all, the job of a vertex shader is to calculate the X, Y position and the Z, which is like the depth for depth sorting of each vertex. You got your per vertex UV. If there's other stuff you need, normals, you can also put that there. So often, and that's the case in this slide, there's often you'll be able to just take data from the mesh, which is what's here labeled as V. The V, and for reference sake, the V in the function is actually passed as an argument called appDataFull, type appDataFull. So that's what comes from the mesh. That's exactly what comes from the mesh. The value in UV, therefore, is like whatever is set to in Blender. And so what this is doing here is it's taking that value from the mesh and putting it into the V2F struct, which is the output of the vertex shader for use later on, because you're going to want to use the UV to do texturing. Click. Okay. Uses of a custom vertex shader. I'll cover some of these later on, but wind effects, extruding the mesh along the normals is a common trick to do outlines. So to do that, you could, any other sort of animation, and any complex calculations. Most meshes have way fewer vertices than pixels, so you can sometimes gain a lot by doing the complex math inside the vertex shader. So the math is already done when the GPU goes through each and every pixel in your mesh to actually draw them. So what is a fragment shader? The fragment shader, also known as a pixel shader, it controls the color of each pixel, or fragment as it's called sometimes. So the fragment shader, in contrast to the vertex shader that ran on each vertex of a triangle, The fragment shader runs on each pixel of the triangle. And it is often the place you'll want to sample textures, which is what this code does here. That uses the text2D function to sample the texture using a texture, and which is called main text here, and the UV that, if you recall, we saved the UV from the vertex shader early on. So the UV and normals are calculated by the vertex shader, and they are provided but interpolated to the pixel being rendered. So your mesh contains only the vertices of the triangles. And so you might have UV of 0, 0, 0, 1, and 1, 0 on this triangle. But in your fragment shader, it'll actually give you a value of the UV that wasn't in your mesh. It might say like 0.3, 0.6. And that's because that particular pixel of the triangle got interpolated to that UV value. And so you can just pass that straight into the texture, and that's the exact right pixel of the texture to sample. So, and of course, for fragment shaders, you can paint any pixel within the triangle. You can't paint pixels outside the triangle. So if you want to do like a weird glitch sort of effect, you will need to do something a little bit more than just a custom fragment shader for that sort of thing. Let's see. So, yeah, there's other uses of fragment shaders. You can pretty much anything. Customize lighting, extra textures, noise, animations, ray marching, skyboxes. If you browse Shader Toy, every shader on there is just a fragment shader, because the vertex shader is paint inside the canvas. It's always a quad, so the vertex shader isn't even something to let you customize. Every shader in Shader Toy is a fragment shader, and you can see all sorts of crazy stuff there. So I'll just kind of say anything's possible in a fragment shader. So when to use custom shaders? So I think one common case is optimization. So I'll cover this a little bit more later, but yeah, basically sometimes you can, with a very small amount of code, you can go and take something that would have needed like 10 different materials for something and make it into one material, maybe by using something called a UDIM. A UDIM is just basically when you have UVs, usually your UVs are 0 to 1, you can go and make a UV that's like 10 or 20, and it'll wrap the texture, so it still acts like 0 to 1, but then you can take that extra data, like how many 10s is it, and you can go and use that in the shader to do something. So for example, it could be like every multiple of 10, you change the color, and that what might allow you to use one material where you'd otherwise need like 20 materials, for example. And I think there's a trick that's been mentioned before about scale, using, you can take something that would need 20 different meshes and use the scale of the mesh to sort of pick out which one you want. So other things, animation, I've covered that before. It can allow for optimization, because instead of needing 1,000 animators or whatever complex animation setup you have, you just customize a shader, and the CPU doesn't actually have to do any work at all. So what are the other things? Immersion, we talked about custom fog effects, skybox, rain, snow, post-processing, that raindrop shader everyone likes. Can add immersion, wind. I don't know if stencils are kind of a cool thing that can add immersion sometimes. You can make something, make an outdoor scene, or all sorts of immersive possibilities. Customization, I'll kind of go through this. Yeah, so basically allowing for extra texture maps can be quite useful sometimes, like detail maps, or maybe different types of masks. You might want like a dirt and like a grass texture and kind of mask between them, or you might want like a decal if you ever want to like paint something on one particular wall but not the other. Actually, the TLX room, Orals explained, use a technique kind of like that. So let's see. Interactivity, so you can make overlays, subtitles, target indicators can be useful in game maps. You might want to like point to where a target is, and let's see, screen space effects, transitions, like all these things that, like, if you've ever been to like a really nice looking map, they kind of those extra little things that you'll often see maps do, that like fade out the screen nicely, or transition something, or when you get hit with a sword, you get a little bit of like a distortion effect because you should feel that you got hit by something. So all of these add a little bit of something to the environment, and I would encourage the use of shaders in these sort of cases. So, draw calls.
Stay hydrated.
Stay hydrated. It's very important. All right. So, what is a draw call? So, what a draw call is a draw call is basically a list of vertices and faces, triangles, getting sent to the GPU with a particular material and shader bound, and all the uniforms are set. These are all things that engine like Unity will have to do every single time you try to draw a mesh. Well, the vertices and triangles often be cached in the GPU, but you still have to like tell it which one to use. You have to bind the material. So there's a bit of work that's done for every draw call. So basically, one thing that you can that a shader can do, kind of like I mentioned earlier, is if you can get a single material and shader to do everything, you're going to be reducing the amount of time the CPU has to work. And in fact, you might allow for batching or instancing to work, which will again reduce the amount of work the CPU has to do. So that's kind of where shaders are relevant to the number of draw calls. But yeah, this is the CPU side. So what actually happens on the GPU when you do a draw call? So first of all, you're going to have the vertex shader run for every vertex in your mesh. And after the vertex shader runs, there's something called a perspective divide, which I'll cover later, but that's technically not part of the vertex shader. But first, we need to talk about spaces. So, and just as a reminder, a vertex shader's job is to transform vertex position vectors from object space to clip space. So what is a space? What does a space mean? Well, let's start with vectors. So what is a vector? Oops. So vectors are directions. So a direction would be basically the way something is facing. So in this case, a direction vector on this image is this arrow pointing up. So it's, let's say in this case, up would be represented as float 4 of 0, 1, 0, 0. So let me explain what that means. So a direction vector, let me start over, sorry. A vector is 4 values, so it's x, y, z, and w. In a more general space, you might see other sizes of vectors, but for the purpose of this talk, I'll just talk about 4D vectors and sometimes 3D vectors. So 4D vectors have x, y, z, and w. 3D vector would just be simply float 3 of x, y, z. So a direction vector I will refer to as a 4D vector of x, y, z, and 0. And sometimes float 3 just x, y, z. So this is sort of the notation. You'll see the words float 3 and float 4 in shader programs. That refers to a 3D or a 4D vector, respectively. So a direction vector is often normalized. So you might often want, like, an up will be a direction. It doesn't really have a length. It's just up. So in this case, up would be 0, 1, 0, 0. So in something like Blender, which has Z up, it would be 0, 0, 1, 0. But, you know, there could be other directions. Let's see. So a position vector. So a position vector is x, y, z, and 1. So the W component for a position vector is usually 1. And so this vector is, let's say, like 3 meters above my left hand. So my left hand's 1 meter out, 1 meter up from the ground. And then 3 meters above that would be -1 for 0 and 1 because it's a position. So a vector is often stored as a float 3 in structs, but you'll want to add the 1 back when you do math. And we'll get to that in just a second. So a direction is relative to a position. So that's kind of how these two types of vectors interact with each other. And let's see. So transform matrices. So basically a transform is a 4x4 matrix. And really, if that sounds intimidating, I wouldn't worry too much about exactly what a matrix means. You don't really need to usually work directly with the matrix. I'm just showing this here so you kind of have an idea of the type of data that you would find inside of a transform matrix. So a transform matrix contains the stuff that you'll set in your object transform in something like Unity. You'll have your position, your rotation, your scale, and basically the translation or the position offset is in this last column of the matrix. The the rotation and scale are part of what's called a basis, and so that's the 3x3 matrix that's on the left. And the reason for this distinction, if you work with a direction vector, you actually don't want the position to be offset. If I go up, I'm like, well, what's up relative to you? You wouldn't go and be like, well, it's 0, 1, 0, 0, but actually plus some position offset. It would just still be up. So that's why the translation is in this last column, and it can be ignored when you deal with direction vectors. And the basis applies no matter what type of vector you're using. So yeah, so your 4x4 transform matrix is used by positions, and the 3x3 basis matrix is for the scale and rotation. And you'll another example of the distinction between position and directions. So a vertex position, like your vertex on the mesh, will be sort of a position vector, but your normals, your tangents, those sort of things are kind of more like direction vectors. So let's see. Yeah, and you can, of course, convert from a 3x3 to a 4x4 to a 3x3 matrix. HLSL will do that automatically for you, but that's what that 0 at the last coordinate does. So what is a space? I talked about earlier this idea of object space and clip space. So what is object space? So object space is a space relative to an object's pivot. So this is like when you edit a mesh, whatever up in the mesh is. So for a humanoid, let's take a humanoid avatar, my head will be up in the Y direction, and if I'm lying down or sideways, my head is still up locally, potentially. Or maybe a better example is an airplane. An airplane's forward vector is like the nose of the airplane. The airplane can be facing any direction, but no matter which direction the airplane's facing, the nose is always at the same object space position. So there's world space. World space is relative to the world. So if a plane is backwards in the world, its nose is suddenly going to be at maybe -1 instead of +1 in the z-axis. So that's so that's the world space. And then there's camera space. That is relative to where the camera is. I couldn't really show it on this picture because you can't really tell where I took this photo from. I wouldn't be able to see its own position. So I just kind of put the cursor up there. But up is up, right is right, relative to where the camera is, not relative to where the object is. So finally, there's clip space, which is sort of a flat 2D projection. And clip space is a bit funny. It's represented as X, Y, Z, and W. The W is called a perspective divide. And the GPU will internally use that to divide X, Y, and Z to produce the perspective effect. So basically, the last sort of space that's interesting is called screen space. And screen space is what you get when you get X divided by W and Y divided by W from whatever you get in clip position. Anyway, this is all a bit technical, but just kind of remember there are different spaces, the different reference points for your object to be in, essentially. And for some effects, it might be interesting to know, but most of the time, Unity does this for you. If you call the Unity object a clip pause function, you're getting a clip space position, and you can pretty much just end with that. So it's another thing. Clip space is sometimes called like post projection. Like the projection matrix is what takes something from camera or view space or camera space into clip space. And another thing to mention, like this clip position is sometimes just referred to as position, or in OpenGL it'll be GL position, or in HLSL it might be called SV position. Those all kind of refer to the same thing. So it kind of goes by a lot of different names, but it's all referring to this concept. So yeah, let's see. Yeah, and also one more note, this is in surface shaders, which we'll cover later. You don't even need to worry about this. This is all done for you. So what can we actually, what's the point of talking about spaces? Why is it interesting? Well, so depending on the type of effects you want to do in your shader, you might want to use object space. You might want to use for like, let's say something is like locally spinning or deforming vertices relative to the mesh, you wouldn't want that to deform in a different direction depending on which way your mesh is facing. So that would be an object space thing. But sometimes you want something world space. For example, like gravity, if you want something like float away from gravity, or you want wind or rain. You don't want your, if you turn your object upside down, you don't want the rain going up. You still want it going down. So that's why you want to work in world space for that type of effect. Then there's camera space. It's actually not that useful usually to think of things in terms of camera space, but especially in VR, sometimes you want things relative to your camera and not relative to screen space, because screen space will be different in each eye. So that's something to keep in mind when you work with VR. But screen space you would often use for like post-processing types of effects, things that run for every pixel. So, all right, let's go back to what we were talking about earlier when I said, here, let's first talk about spaces. Now we've kind of talked a little bit about spaces. You know, your vertex shader runs and it transforms a vertex from object space to clip space. The perspective divide transforms from clip space to screen space, and now you've got a bunch of triangles glued to the screen. That all of the depth has kind of been forgotten at this point, and now the GPU can go and figure out every pixel in those triangles on the screen, and those are called fragments. Each pixel is then tested for depth using that last z value, the z divided by w value earlier. That actually, you know, if something is behind something else, you don't want to show it. It's often referred to as clipping. If you have two objects of the same z, that would be called z-fighting. That's what that depth and z value is used for. Other than that, it doesn't really matter. So yeah, you can test for something called stencil, and you can use the stencil and depth to make certain types of effects, so it is worth knowing about it. So then, now we're at the fragment shader. The fragment shader runs in every visible fragment and produces a color, and the color can be blended. If you want something transparent, that's done by calculating the color of the thing that you're rendering, and then blending it with the thing behind it using the alpha value. So what is a use for a custom fragment shader? Or sorry, yeah. Fragment shader will sample textures. It will calculate lighting. And one thing to note about lighting, you don't have to do all of the lighting math yourself. Doing lighting math from scratch is quite involved, and I wouldn't recommend you start with that. If you're interested, Cat-like Coding has a great example, has a great tutorial series on building up a lighting function, but they do start with just using Unity's built-in lighting function, and you can call it just like you would any other function in your program. But you can also go and start with surface shaders, which we'll cover later. And with surface shaders, you don't even have to worry about lighting. That's all handled for you. You can still choose to implement your own lighting function, but you're not required to. So I'm not going to really cover exactly how lighting works. I don't think I can do a better job than what Cat-like Coding does. So I would highly recommend checking that out if you're interested in custom lighting. So yeah, then you might want to do reflections, refraction using the reflection probe. That's the cube map. The actual code for some of these things is actually pretty straightforward. The sampling cube map, you just give it a direction, and it gives you back the color of the reflection probe in that direction. So some of these things are pretty straightforward to do. You might want to do some other custom patterns. So then there's more advanced uses of fragment shaders, tune ramps, light maps, ray tracing, ray marching, grab passes, water, fractals, whatever. I mean, the list is infinitely long, basically. But some of these things aren't too hard to do. I would, you know, there can be cases where something like ray tracing might be useful. For example, a skybox which uses a ground plane, so then you can make it look like there's actually a flat ground, even though it's a skybox. Let's see here. But first, let's talk about math. This is everyone's favorite subject in the room, I'm sure. I'm sure you're all going to be really excited about this. But math is really important for all aspects of game dev, and you should not be afraid of math. Math is awesome. Math is amazing. Anyway, so here are the things we're going to talk about. So we're going to talk about applying matrices to vectors, which is basic linear algebra, dot product, cross product, sine, cosine, which is trigonometry, and then some custom sort of shader concepts, LERP, smooth step. These are really useful, so it's good to learn about them. So yeah, if you haven't remembered your high school math class from 10 years ago, which all of this would have been covered in, don't worry. There's plenty of resources online, and that's why I'm covering this a little bit, just so you're familiar. But I need to quickly resolve the Steam VR issue. Oh dear. Let's see. All right, I'm cleared up. That was a bit freaky. All right. So linear algebra matrix operations. We touched earlier on vectors and transform matrices. So applying a matrix to a vector is basically transforming that vector from one space to another. That's the best way to think of it. That can be done with a mul function. The mul function, it does matter which order you do them. Matrix does matter which direction you apply the matrix to the vector. For our case, and for most of what you do with shaders, you're always going to put the matrix first and then the vector. So, and yeah, so HLSL, you just call the mul function. And yeah, the example is, for example, you do mul, you would pass in this unity object to world, which is a matrix that transforms from object space to world space. And you put in your in this case, a position vector, because it's 0, 0, 0, 1. I want to find the center point of my object in world space. So that float 4, 0, 0, 0, 1 defines an object space position. Run it through the matrix, you get back another position vector. But I might only be interested in the x, y, and z coordinates. Maybe I want to throw away the last one that's always there. So I can do something called a swizzle. So I just say .xyz, and that means just give me the x, y, and z coordinates, and don't worry about anything else. So you can also do other swizzles. You can do x, z, y to flip like Blender coordinates if you want to do something like that. Swizzles are useful. It's good to know about. You don't usually have to do too complicated swizzles, but they're there. It's a tool. All right. So vector operations. Normalize. Length gives you length of a vector. Unit vectors are defined as vectors with length 1. Normalize, if you have something you're not sure if it's a unit vector, just call normalize on it. It'll make sure it's a unit vector. And that is often good practice. For example, if you take a normal and you set your like v.normal, o.normal equals v.normal in the vertex shader on each vertex, sometimes the interpolation process will cause it not to be a unit vector on each pixel of your triangle. If you're ever worried about it, just call normalize on it again. I know it's an extra operation. Don't worry about optimization right now, but that's a whole other subject. Just call normalize. It'll make your life better. So it's a good function to know about. Dot product. Once you have things that are unit vectors, you can do some really cool stuff with dot product. So the dot function takes two vectors, and if they're both unit vectors, it returns how much they point in the same direction. So if two vectors point the same way, it's 1. If they point orthogonally, that's the right angle, it's 0. If they point opposite direction, it's -1. And if you've ever attempted to write custom lighting models or do anything lighting related, the dot product factors in heavily there. You can basically, you can make a pretty simple lighting function just by running dot and doing some stuff with that. You can pass the result of dot through a lighting ramp and make a custom tune shader. So it's pretty useful. And if x and y are not unit vectors, dot will also multiply the result by the length of each vector. So it can get a little bit confusing. One thing that's interesting, it's kind of interesting identity that we can cover, is that length of a vector is the same as the square root of the dot of a vector with itself. What does that mean? Well, the vector in itself always point the same way because it's the same vector, so that's 1, and multiplies by the length, multiplies by the length again, therefore it's the square of the length, and so you can take the square root of that, and it's actually the same as the vector length. So that's kind of an illustration of how this concept works with the dot product. And sometimes you want to let's say I've got like two vectors that kind of point at an angle. Taking the dot of a unit vector with a non-unit vector will sort of like project the non-unit vector onto the unit vector and tell you how long it is how long its like shadow is on that whatever other object. So there's a lot of other stuff. Again, tons of resources online to read up on linear algebra concepts. Most of what you probably will end up doing isn't too complicated, so I wouldn't worry too much if this is a bit confusing, but it's here. It's good to know. Cross product. Cross product is well, let's start by defining, again, orthogonal unit vectors are those with a dot product of 0. So they're exactly 90 degrees apart on some axis, not facing the same direction and not facing the opposite direction. So the cross product of two unit vectors produces a third unit vector orthogonal to, let's do it like this, orthogonal to the two vectors you put in. So, and a cross product only works for float 3s, 3D vectors. So you can use .xyz to do it. And one of the common cases, and the reason I'm covering this, is that this can be used to calculate what's called a binormal from the normal and the tangent. And so if you ever take a mesh normal and a mesh tangent and you cross product the two, you're going to get a binormal. And those three together can be used to make a matrix and a basis matrix, which you can then make a coordinate system relative to that pixel of the mesh. And that allows all sorts of interesting stuff that you can do. Once you have like a custom space, you can transform stuff into it. And yeah, so basically cross product is often used for sort of constructing this binormal vector from the normal and tangent. That's where you're likely to see it. So trigonometry, sine and cosine. So you can use those to make a rotation matrix. You can use dot of two unit vectors instead of running cosine. Sometimes you're given already two vectors, and instead of like converting them to an angle and back, you can just call dot, and that gives you the cosine. So you don't always have to use the trigonometry functions directly, but it's good to know that they exist. So yeah, the inverse, sort of the inverse of sine and cosine is a tan 2. So a tan 2, you give it the cosine, you give it the sine as the two arguments, and it actually gives back the angle that produced those two things. But this is not magic. A tan 2 has flaws. You have to be careful about it. And one of the big issues with it is it will have a discontinuity at 180 degrees. So it's good. Sometimes you'll write code that uses like sine, cosine, a tan 2, and you're like, well, wait a second, I could have just taken the x and y coordinate of this unit vector and just used that instead of the sine and cosine. And it works out often that you don't even need the angles in your math. It'll just, just take x and y and do this or that with it. So it's good to know about. It's also good to consider that there are flaws to using angles because of the discontinuities. There's also a cosine, arc cosine, however you want to call it. And that can be used for, like, for example, like the vertical angle. If you want like a 3D sphere, there's two angles. There's like the latitude and longitude. So one is with a cos and one is with a tan 2. So, but yeah, again, you have to consider when you want to use angles and whatnot, and be aware of the fact that the discontinuities might cause like the texture maps to be sampled incorrectly and stuff like that. But there are a lot of uses for it as well. And if you want to make a matrix using the sine and cosine, there's actually a function that I always copy that's like, it takes an angle and an axis and produces a transform matrix. And you can essentially, again, use this to define a custom space and then transform stuff into your like custom reference point. So lerping, interpolating. Oh, actually, sorry, I stuck on a random thing here. So, multiplication is useful, can be done on floats, but also can be done on vectors. And when you do it with a vector, it just multiplies every component in the vector. So you can multiply, for example, a vector with 2, and it'll essentially make the vector twice as long. It'll scale it. You can also add two vectors together. All of these things can be done. Multiplying two vectors is kind of weird. It just multiplies each number of each axis. So it's not clear that it's not commonly used, but that's what it does if you put star. So what does it mean to lerp? So lerping interpolates from point A or from some value A to some value B. You often see this maybe with colors. So you might want something like, I want something green, I want something orange, and then I want to make a nice and smooth transition between the two. You put lerp of green, which would be float 4, 0, 1, 0, 0, 0, 1, 0, 1, and orange would be like, whatever. And you would pass those two into lerp with a interpolant, and it'll go from 0 to 1. One thing to note, this third value in lerp is like, if it's 0, it returns A. If it's 1, it's B. If it's in between, it's in between. If it's below 0 or above 1, it'll actually do kind of usually undesired stuff. So the next functions, so yeah, anyway, question mark colon. I'm just putting this here because a lot of people aren't familiar with it, and it shows up a lot in shaders. I don't necessarily suggest that you use it, but it's there, and it's good to know it exists. And what it does is it chooses, depending on the first condition, it might be the thing after the question mark, or it might be the thing after the colon. It'll be one of those two results. So it's kind of used in place of a LERP, where you don't actually want the in-between, but you just want to have either exactly the first value or exactly the second value. Step. So the step function is 0 until x hits a, and then it's 1. So it's good to view this function as like a subscript. If you ever worked with the math functions, it's like step subscript of a of x. So it like a is the stopping point, and then x is 0, 0, 0, 0, and then 1, 1, 1, 1, 1, 1, 1. So that's what step is. This function smooth step is really useful and quite commonly used. It's good to first talk about step, because smooth step is basically, it's step, but instead of a single value where it jumps from 0 to 1, it's kind of like 2 stopping points. If you've ever used like a gradient editor, for example, this is kind of like, it would be like if you put like 2 stopping points in your gradient editor and like had 0, 0, and then like dot and dot, and then like, and then 1 the rest of the way. So yeah, smooth step basically, and smooth step can often be used as the third argument to LERP, and it nicely avoids the whole issue of, well, what if x is less than 0 or greater than 1, because it makes sure that the resulting thing is always between 0 and 1. So smooth step is a really nice function. It solves a lot of issues. You can pretty much put anything there and put some like stopping points for a and b and put in whatever x you want, and you're always going to get something nicely between 0 and 1. Yeah, and shaders come with tons of functions by default. Like, literally has a built-in function called reflect and refract, and if you give it the vector and your normal vector, it'll just tell you where it reflected or refracted to, and you can just pass that straight into the cube map. So you, like with 2 lines of code, you can pretty much write your own like, you know, reflection or refraction type function using a cube map. So it's pretty simple. I'm going to put a link later on in the slide, but there's you know, HLSL Microsoft documentation has like a list of all the functions there, and so highly recommend reading through that if you're ever interested. Surface shaders. So now we're going to write our own. I'm going to show you a little bit how to make your own shader from scratch with no knowledge. So if you recalled, I showed an example shader earlier, and there's a bunch of lines that, you know, you probably didn't remember any of that. I don't expect you to remember any of that. That shader was unlit, so not only was it like, you know, there was a lot of code you'd have to customize, it was completely unlit, there was no lighting. If you brought one of those things into this room, it's going to be like bright as the sun. So and writing sliding code from scratch is challenging, and you can follow the cat-like coding examples and call the Unity's lighting function, but that's still a little bit involved. There's, you know, you don't want to have to do that work every time you write a shader. So, and I said shaders are supposed to be easy, so we were fortunate. There's a thing in Unity called surface shaders, and surface shaders take care of all of the annoying stuff for you. So I highly recommend starting to learn using surface shaders. And it also happens to be what Amplify uses for a reason, because it's, again, it does all the annoying stuff for you, and it's nice and simple. So, you know, if you even use Amplify, you're actually using surface shaders underneath. So let's go and make a custom surface shader. So basically, if you ever go and right-click on your asset in your project assets, you can go to Create, go to Shader, Standard Surface Shader, type in a nice file name, and hit Enter, and make sure you have Visual Studio Code or another equivalently good editor. And if you double-click that, you'll get exactly what I put here in Unity 2018. I removed the comments and white space to make it fit on the slide, but essentially, this is what you'll see. This is a so let me quickly explain the different parts. There's the blue boxes, the gray blue boxes are the properties and uniforms. Just like we saw earlier, this is the inputs to the shader. These are the things you would set in the inspector, and they'll show up in there, and you can just use them, like your texture, your glossiness slider, your color. These all get fed in as inputs there. It also has this nice thing called Unity Instancing Buffer Start. It's just handling that for you. Anything you put in there can be done with GPU instancing. So you're free to use that to optimize stuff later on. And there's the thing I referred to previously as V2F. That is the result of the vertex shader and the input to the fragment shader. That is here called struct input. And so the stuff inside struct input are sort of computed by the vertex shader. And even better, Unity will calculate this stuff for you. You don't even have to write the vertex shader. You have to use the correct names. So if you go to the Unity surface shader documentation, there's a list of like official names of things you can put in the input struct. And just by writing a variable with that name, it'll use that. So I brought here a little example program that I was. So this is a modification to this. I added a few extra float variables, and anyway, I don't. Yeah, basically, oops, here it is. Brought in a little toy. So this is what happens when I add these lines of code to the new Unity surface shader. So I made a little Fresnel. I just copied a code sample online for this. It's a few floating point values to define how the Fresnel works. And the vertex motion I'll get to in the next slide, but that's also on here. And then if you see, there's a bit of a scrolling effect with blue scrolling, and that's handled by these last two lines on the slide. So I get the sign of time and the world position, the y world position, and I store that in a variable. I multiply it with itself to make sure it's always between 0 and 1, because sign gives you a variable between -1 and 1. I don't know if this is readable on the video, but I'll try to, yeah, anyway. Yeah, so basically, I was able to make sort of a scrolling, like vertically scrolling effect by making sure it's positive and then using the PAL function. The PAL function always needs a positive number. It'll sometimes malfunction if it's negative, so always make sure it's positive. And then a power, so I made to the 10th power, and that produces kind of a cool like scrolling effect over time. Sometimes a little blue thing will kind of slide down. So that's that. So that's an example of something you can customize with the surface shader. The Fresnel, I calculated something in the vertex shader. So I added something that says like o.Fresnel equals and some formula I copied from the internet. Let's go, I'll cover a bit more detail the vertex shader part of this. So because this is sometimes a little hard to find the exact documentation for this. So the vertex shader for the vertex motion, the thing that made that sphere move up and down. So this is a, so these are the only changes I made from the right-click new surface shader. So I added 2 new properties. So it's a direction that the sphere moves. Like I want to move it up, and then a period, which is how many seconds between pulses of the sphere. So I added in the properties that made it work in the inspector, so I could just go in the inspector and set it. And then I had to also add the float for the direction because it's a vector, and the float for the period because it's a float. It's a single number. And I added those to the uniforms part of the code. Then I added a vertex shader to the hash pragma surface line. And this is just something you copy and paste. You don't have to. I wouldn't suggest remembering this because the syntax is a bit confusing with this stuff. But basically, just know you can add this little thing. You can add a bit of extra stuff into the pragma surface, namely vertex:vert, and add shadow is important. That's like, again, surface shaders do a lot of stuff for you, but you have to tell it to do the stuff for you. And so the add shadow means if you don't put the add shadow line, it'll assume your object doesn't move and use like a default shadow. And so your shadow is not going to move, but your sphere moves, and it'll look kind of weird. So writing add shadow fixes that, and it makes the shadow work correctly. So good to do that if you do anything custom in the vertex shader. And finally, the actual code in the vertex shader. So let's look at what that does in more detail. I'm going to zoom in on that. So the vertex shader, again, first 2 lines, it's a function declaration, some input, in, out, out. This is straight from the Unity documentation. I don't suggest you remember this. Just know that there's 2 lines of code you have to write here to start the vertex shader. So we declare a new variable. I'm calling it rolled up because I wrote this before I made it the parameter. Now, a custom thing in the inspector, it doesn't have to be up anymore. But I left the variable with the old name. So this is taking that direction vector we specified as a uniform input. and multiplying it with the world to object matrix, because I wanted my direction to go up and down regardless of which way I hold the sphere. You know, so it always goes up and down even if I put the sphere upside down. So I just decided that would be cool, that's why I did it that way. And that gives you a direction vector in world space. Now we want to calculate the actual like motion, and so I like to use sine. I think sine is a really cool function because it's like always periodic. You can pass the time into it, and you know it'll change over time, but always be within like some nice range of values. And because of how sine works, it wants an angle, and I want time aren't really the same thing, so I just multiply by 2 pi. And I divide by the period, because if you multiply it by frequency, and so if you want something time-based, you divide by the time. Kind of frequency is 1 over time. So it's that sort of quality. So finally, I take this x value, which is this periodic -1 to 1 value, multiply it by the direction, and that'll now produce a direction that's scaled by this number between -1 and 1. Sometimes 0, sometimes the direction, sometimes negative the direction, and in between. And I simply add that to the x, y, and z of the vertex. Now note that I could have just left it as plus equals without doing dot x, y, z, because the w for a direction vector would be 0. But just to be safe, I did dot x, y, z. That means I won't mess with the w value. So, yep. And that's basically what a vertex shader would look like. So, in conclusion, I'll cover a few other things that shaders can be used for that I think are really good to know about. But first, let me hydrate myself. All right, so what is a GPU actually? What is in your RTX 3090? Well, it's basically a processor, much like your CPU, much like your Intel processor or whatever else. Its job is to take instructions and execute them and calculate whatever result you desire. But unlike a CPU, the GPU is designed to work with bulk data. So instead of a CPU which runs 1 line of code at a time, you know, the GPU is designed to take 1,000 pixels at one, or probably 32 by 32 or whatever block size, and process them all at the same time. So it's designed to do a lot of stuff of the same type at the same time. So, for example, you might want to take all your vertices at once and then run the vertex shader on all of them, or take all the pixels at once and run the fragment shader on all of them. So, you know, if you think of using if statements, that can actually slow things down significantly, because if you take multiple branches, it'll have to process both branches and do a bit of work there. So it's good when you think about writing stuff for the GPU to think of it processing data in bulk. So, and in terms of computation, it's good to think about the inputs and outputs of what you write as a shader. So, you know, in the case of your traditional vertex fragment shader, your inputs to the vertex shader is your data straight from the mesh. The output is this v2f struct, that's sort of this temporary data that goes into the fragment shader. And then your fragment shader's output is the colors and the depth value as well. So, yeah, so the inputs, well, in addition to the mesh data, you know, you also have uniforms. There's a lot of different types of uniforms. Uniforms just mean anything that's the same for every vertex of your mesh, or every pixel of your mesh. And also, of course, textures. Textures can have lots of data in them. Those are also inputs. So, and then other types of uniforms. There's actually a lot of different places uniforms can come from. There's material properties, instance properties, material property blocks in Unity, which is like a per mesh thing, like set by animations, for example. Uniform arrays, which you can set using Udon. And then, of course, there's a lot of built-in variables, like where's the light, where's the camera, and time. The time value is a built-in one. So now we have the outputs. The outputs of a shader would be, you know, your colors, your depth, if it writes a stencil, it might write the stencil as well. Those are all things that like shaders can essentially update. It's much fewer things than you would see as inputs. There's a big, I'm not going to go into it, but if you use compute shaders actually allow you to write the same types of things that you can input. So they're very powerful, but I'm not going to cover that. So, and if you want to actually use shaders to compute stuff, you can actually use cameras, custom render textures, and like I mentioned, compute shaders. So those are all ways that you can capture the result of a shader instead of just displaying something on the screen. So and then, yeah, of course, you can then take that data back to the CPU using like get pixels and Udon or any other sort of async readback. So cameras and render textures, they're cool. Simulations, game of life. I mean, we have some people in the audience who make neural networks. That's another valid way to use them. Encoding, decoding data. So if you've ever seen the system called Shader Motion by LOX9973, it actually takes pixels from a video and reads those in the vertex shader to do mesh deformation using the same techniques you would use to make a skinned mesh work. So there's lots of different uses for processing data. And I'm not expecting you to sort of learn this from scratch, but it's good to know that it exists. Good to sometimes think about like when it might be an appropriate solution for the type of problem you're doing. The GPU is very powerful, and you can do really cool stuff if you make use of the power the GPU provides. So in drawing onto text. Okay, with that said, I have a ton of really useful links. I'm just going to quickly test this out because it's malfunctioning. Okay, it does work. Okay, so with that said, there are some really useful URLs to reference. Bookofshaders.com, it's a great website. Cat-like Coding, it's really good tutorial, especially if you want to learn how Unity lighting works. Shader Toy, pretty much everything under the sun, but it's all done in the fragment shader. So they actually write their own ray tracing or ray marching, but there's tons of interesting stuff in Shader Toy, and I highly recommend, again, like if just looking for stuff and copying the code and playing with it. And of course, you have to convert from GLSL to HLSL. That's a pretty straightforward process for that. There's another thing. If you work with Unity, but even if not, Unity has all the source code to their shaders online, available to download in MIT license. You're free to copy whatever you want from it, but they don't give it as part of the Unity editor for who knows what reason. Instead, they give you this weird 100 kilobyte zip file you have to download from a special place. I recommend downloading the zip file if you do any work with shaders. If you extract it, there's two folders. There's default resources extra. That's where the source code to all the built-in shaders, like standard. You can actually look at some of the code there. And CG includes, which is all the things you do pound includes, which I didn't cover in this talk, but pound include, hash include gives you access to built-in functions, so it's useful. Or you can separate your code into multiple files. So CG includes is all of those files. It's all there. So highly recommend using Unity shader source code as a reference. And it's not on, the stuff online that's outdated or just not there. You have to just download it yourself, unfortunately. I don't know why Unity doesn't publish it. And then, of course, the Microsoft HLSL documentation, it's a great place to find information. Most of the stuff, you'll just Google it and it'll show up. So you don't need to copy these links necessarily, but there they are. So yeah, I appreciate everyone listening to this talk. I hope, even if you haven't learned everything, because I don't expect anyone to be able to learn all of this stuff. I haven't even. But if you learned even anything at all, I hope this is helpful. I hope it makes people less afraid of writing shaders. I don't think shaders are something to be afraid of. I think they should be treated as a tool, as something you can use to make your content better. It's definitely not required for all types of content, but it is a tool. And don't be afraid to ask for help. Again, don't be afraid to Google for help. Don't get frustrated. It took me a year to get even basic familiarity. So, yeah. Any questions?
Do you want to ask questions, or can I go ask questions first?
I think you're supposed to step into a special box.
Yeah. It's over here. There is a spot over here. I'm not by any means a shader programmer, but I do some things from time to time. And I'm not smart, so I could have probably Googled it, but since you are here, I wanna ask a question. What the hell does a uniform mean, and when should I put it in front of a thing? Because I usually
Okay.
don't do
I
that.
had that in my notes and I forgot to mention it. Good question. And let me see if I already wrote the answer to that question. No, anyway, I'll just explain it. So this is actually one of those dialect differences between GLSL and HLSL. It's actually really good to be aware of. So in HLSL, anything declared in global scope that is outside a function is uniform by default. And that's really important to know, especially if you go and say, I want to write a constant. So if you just go and naively say like const float pi equals 3.1415 semicolon, that variable is going to be 0 when you run the shader. Do not do that. Always say static if you don't want it to be uniform. Because by default, it's uniform, which means it'll expect you to set in the inspector, and if you didn't, it's going to be 0. So yeah, that's why you often don't see uniform before variables in HLSL, because it defaults to uniform. So it's good to be aware of that. In GLSL, it defaults to essentially what HLSL calls static. So if you write a global variable, and you'll see some shader toys do this, you just say like float foo equals 5 semicolon, that declares a sort of just a temporary scratch space to like, set some value or make a constant. So in GLSL, default is static, and you have to I don't even know if you can say static in GLSL. You just don't say anything, and you have to say uniform in GLSL to make it a uniform. But the term uniform refers to both types of, refers to those variables, even if you don't write the word uniform in front of it. It's still the same for every pixel of your shader, hence it's a uniform.
Okay, yeah, that makes sense. It makes sense that it's implied because it didn't break anything, right? But like I never wrote it explicitly in this case.
Yeah, you don't
thanks.
have to in HLSL. It just does it for you.
Are you muted?
Are you on the correct
I can't hear you.
Sorry, I'm back.
Oh,
Here
cool.
I am.
I hear you now.
So, so there's a pretty mind-blowing demo that Inigo Quiles, one of the co-founders of ShaderToy, did just within the last couple of weeks, where he's able to essentially create an entire scene using SDF.
Oh yeah.
and
IQ is amazing.
But I assume that, like you said earlier, that's sort of painted onto like a 2D canvas and gives the illusion of like a 3D scene. But
Yeah,
have you
that's
seen? Are there any like VRChat worlds that just are kind of like from the demo scene, just entirely shaders and?
Yes.
And
there
yeah.
is.
And is there any?
Have you seen Treehouse in the Shade? Treehouse in the Shade is an amazing demo of what you can do with shaders, and some of those are actually straight from ShaderToy. So there's something I didn't cover in the presentation, but the fragment shader can actually write to the depth value and can produce things that have depth in 3D space as well. And a lot of times, if you transform something from ShaderToy, which I didn't cover, but one of the techniques that you can do when you're translating stuff from ShaderToy, look for the ShaderToy using variables RO and RD. Those are usually the ray origin, which is the camera position, and the ray direction. That is the direction from the camera to that pixel of the material or the object. And there's often some camera code before that. If you want to port it to work in VR, just delete all the code before the RO and RD, or all the camera-related code, and replace RO with underscore in Unity underscore world space camera pause, and replace RD with normalize of world pause minus, or mesh.world pause minus world space camera pause. Yeah, basically, if you replace those two things, you'll essentially get something that works in VR in stereo, because each eye will have its own position and the math just works. So,
oh, awesome.
Yeah. And the depth thing, if you want to calculate depth, there's a process where you can set something called SV depth. And if you assign SV depth to the correct value, that has to be like, there's a function that like converts to like linear depth from 0 to 1, and if you assign the correct depth value to that SV depth variable, it'll actually clip with geometry. You'll actually like put your hand into it, it'll like clip into the stuff correctly. So there's a process for that. I can't tell you offhand exactly how to write that code, but it's not too bad, and once you do it, it works.
Yeah, just a quick follow-up to that, because since it is possible, then is there like a bare minimum of like geometry that you need to just have the avatars moving around? Because I can imagine like with creative coding, you're able to do all sorts of stuff, but it could be sort of abstracted out to the point where, it would be difficult to actually have multiplayer avatars in there. So there's like a bare minimum that you need in order to sort of build on top of that.
It's a bit of a complex question. I encourage you to reach out in Discord or anything if you want to chat more about this. But basically, I mean, if you're just starting with something, I would suggest just taking a cube. just make a cube and put your code on there, and every pixel of the cube will just run the code you write, and it'll look like whatever scene you put in. So
Okay, cool.
if you're talking about making like something like an interactive like avatar that's ray-marched or something, that gets more involved for a few different reasons. You have to actually learn the bone positions, and it's that would be a bit more complicated, but you know, anything is possible if you put your mind to it.
Cool, thanks.
Definitely check out the treehouse though if you haven't already.
Yeah, Treehouse in the Shade. If anyone hasn't been to that world in VRChat, it is amazing. It is probably, especially if you're in VR. I would suggest everyone who has a VR headset, if you've never played VRChat, get VRChat, go to Treehouse in the Shade, and see that world. It is incredible.
Yep. Any more questions? No? Okay, thanks. I don't think Prowler is standing up for a question, so
All
yeah,
right.
I think thanks for the talk.
Thank you. It's been
Thanks,
a
Lyuma.
pleasure to give a talk.
Hey.